now we know what deep neural networks are. We have some idea of how we can specify a loss function, and then with training data, we can minimize that loss function and pick a good set of parameters for our neural network through the process of training with gradient descent. So today I'll just give a few more slides on the training that I didn't get to yesterday, and then we'll talk about convolutional neural networks. As I say, this will be useful for a few other talks that are coming up in this week. As we said yesterday, gradient descent is an iterative method, so you'll start with an initial guess and then iteratively update the values of the parameters until it stops. When do we decide to stop these iterations? We can do so when we've somehow measured convergence, so the difference between successive updates is small enough, or perhaps when the loss is below a certain threshold, or perhaps, and quite often, we would set a maximum number of iterations for our gradient descent, and then we stop after that. Now, something that has also come up in some of the questions and some of the discussions in this series is this idea of overfitting. So if we are not careful, we run the risk of doing overfitting, which is a bad thing. And this is basically when the loss that we are computing on the training set becomes very, very small, but the network is actually unable to do anything useful after that. So if we give it data that it hasn't seen during training, it just is unable to accurately perform its task. And you can imagine that this is something that could happen because when we do training, we are minimizing the loss over the training set. So if that is all that we're interested in, the network can in some sense start to memorize the training set, but it's unable to do anything with data that does not belong in the training set. So that's called overfitting. So one way around this, or to prevent this from happening, is to do something called early stopping. So the idea is basically, as we've also mentioned a few times, is to take a part of your training set and put it to one side, and then do gradient descent on the remaining data, and then use this part of the data set that you've put aside to every so often check how your model is performing on data that it isn't actually using to calculate and to minimize the loss. So that's called the validation data set. So typically what would happen is, if you look at that graph, as the training iterations proceed, our training loss becomes smaller and smaller. That is the thing that we are directly trying to minimize. And then, as I say, we have this additional set of data called the validation set that we don't use that data directly to compute the loss or the gradient. We just use it to check how the model is doing on data that it isn't using directly. So that might be that blue curve. So it is also going down, hopefully. So the model is actually able to do something useful with data that it is not using directly for training. But then at some point, and this is where overfitting might occur, the training loss is still going down. But if we do more and more iterations of gradient descent, the validation loss is now going up, which is a bad thing. And this means that the model is able to perform very well on the training set, but is doing quite badly on data that's not part of the training set. So when that is detected, so we can measure those values of the losses. If that point is detected where the validation loss starts going up, that's probably a good place to stop training. So it's called early stopping, but because we might have not yet reached the best possible, the smallest possible training loss, we might not have yet reached the maximum number of iterations, but it is not a good idea to continue training. Okay. So as I say, we would typically split off a part of the training set for validation, and of course we can also use the validation set to do things like hyperparameter tuning. So if we're not sure how many layers we want in our neural network or what the learning rate should be or things like that, we can also train on the training set and then use the validation set to see how well the model might generalize, change the hyperparameters, do it again, see how well the model is generalizing. If we do that too many times, we of course now also run the risk of overfitting on the validation set. So for this reason, there's a third data set called the test set that we then put aside completely from the training and hyperparameter tuning process. And finally, at the end, see how well the model with its optimal parameters and optimal hyperparameters would perform on data that it hasn't seen at all up to that point. Okay, so with all the label data that we might have available, we would have a training set. This is the one we use for gradient descent. We would have a validation set, which we can use during training for an indication how well the model is, will be able to generalize or to do something like early stopping or to optimize over hyperparameters. And then we have this third set called the test set that is supposed to keep completely separate from the training and validation process. Okay, then just a few other thoughts on how we might avoid overfitting. And so regularization is of course also an important thing. Again, at this point, our loss is defined over the training data, and if we minimize that loss, of course, we'll be able to fit the training data very well, but there is the risk of overfitting. So what people often do is to add another term to the loss function, the function that we're trying to minimize, in an effort to also keep the model a bit more well-behaved, I'll say. So a common thing to do is to add penalty terms to the values of the parameters. So we are penalizing large parameter values. The intuition behind this is we don't want our model to oscillate too wildly between our training data points. We want a nice smooth curve. So you can do L1 regularization or L2 regularization, and that is just specifically how we're going to penalize the values of the parameters. And then we would also typically have this additional hyperparameter that I call lambda, which weighs the regularization term relative to the data loss term that we've seen before. So a bigger value of lambda will mean that I place more emphasis on this term. So if I minimize the sum of them, I'm going to have to work hard to get this as small as possible. If lambda is smaller, it means I'm going to focus more on the data loss. So you can use that to kind of balance these things. So for the first term, we want the model to be able to reproduce the training data as closely as possible. The second term in this loss function says, well, I don't want my model to behave too crazily between the data that I have. Okay, this L2 regularization is closely related to something called weight decay. Basically, if you take this expression for the loss function, and if you recall, for gradient descent, I'm going to calculate the gradient of this loss function with respect to all the parameters, these thetas. And of course, if I consider this term that I've added here, the regularization term, the derivative of that with respect to theta I would be 2 lambda theta. And gradient descent then says subtract the learning rate times the gradient from the current set of parameter values. So one step of gradient descent would basically subtract the learning rate times whatever the data term's gradient is, plus this gradient of the loss of the regularization term, which is 2 lambda theta I. So this basically says that at every step of gradient descent, we're subtracting a small scalar times the value of the parameter. So you can almost think of this as at every step of gradient descent, we're making the parameter a bit smaller. Of course, it depends on what's going on with the data terms gradient, but that's a kind of a similarity. Okay. Then just quickly, something on dropout. This is a popular mechanism for regularization in neural networks, and also, again, to try and reduce the risk of overfitting. So how this works is, you'll remember a neural network, of course, has all these layers. Every layer has a bunch of nodes. These nodes are interconnected between layers. And the idea with Dropout is quite interesting. During training, we basically randomly remove nodes from the neural network with some probability. And so at every iteration of gradient descent, there's a different set of nodes that are being removed from the neural network. And the idea with this is basically that the training process now becomes a little bit more noisy. As we said yesterday, this can be a good thing. Also to prevent overfitting. And this specifically also prevents the network from becoming too reliant on specific nodes or a specific combination of nodes to arrive at its eventual predictions. So it just makes the whole training process a bit more robust and not as sensitive to maybe specific choices of hyperparameters and that sort of thing. People have shown that this also simulates the effect of ensembling sparse networks. So we've seen deep neural networks where all the nodes in one layer are connected to the nodes in the following layer. So it's a densely connected network. Sparse network would be where only some of the nodes are connected to the next ones. So of course, if you remove nodes with some probability from a densely connected network, you end up with a sparse network. And if you do this randomly while you're training, it kind of has the same effect as training a bunch of sparse networks separately and then combining their results to arrive at your final prediction. But of course, now you don't have to do that a whole bunch of times with separate networks. You can train once by just randomly dropping nodes like this. So that's quite nice. This idea of ignoring nodes with some probability is only done during training. At test time, we put all the nodes back with the weights that were learned, and then just have to do a little bit of a scaling to make sure that the values as they are propagated through the network won't be affected by the way that we trained them. Okay. So that's Dropout, and Dropout is also quite common to see in sort of simple convolutional neural networks. Then there's just another thing that I want to mention, which is batch normalization. And the idea is basically to include 2 extra parameters at every layer, or at least where we decide to do batch normalization. So we call these parameters beta and gamma. And then what we do is during training again, we would, this would be specifically for mini batch gradient descent. So we split our training set into smaller batches and do an iteration of gradient descent on each one of those batches. For such a batch, we calculate the mean and the standard deviation of whatever the values would be at a specific layer just before the activation. So immediately after we've done our weighted sum and add the bias, there will be a mean and a standard deviation at every node that we calculate over the mini batch. And we basically shift and scale the activations or the values of the nodes so that the mean becomes 0 and the standard deviation 1. So we subtract that mean and we divide by the standard deviation. And then we rescale and shift by these trainable parameters beta and gamma. So we're basically allowing the network to learn at every layer what is, in some sense, the optimal mean and standard deviation across the mini batch at every layer before it goes through the activation. And there's a few reasons why this is a good idea. One, of course, is that in many of the activation functions that we use for neural networks, they can quickly saturate for very high or very low values. So it might make sense to kind of force all the values at the nodes before they go through activations to be kind of centered around 0, so that when they do go through the activation function, we don't lose valuable information. Okay, so as I say, this allows the network to choose through the whole training process what would be the optimal mean and variance in the hidden layers at every node. And then basically what people have shown through various experiments and things is that this can drastically reduce training time. So we just have that the gradient descent converges much quicker to a good solution. It also allows us to use a larger learning rate. We don't have to make small updates. We can make quite large updates. And again, that would mean we need fewer iterations to get to a good solution. It also acts as a regularizer. So people have seen there's less risk of overfitting on the training set. And in some cases, it can even eliminate the need to do any kind of dropout. So, of course, a lot of these benefits were given by the authors of the paper that came up with batch normalization. So, of course, they would always say that it has all these amazing benefits. Okay, and just again a note, this is what we do during training. During test time, we just have to do a little bit of a trick to make all this work. The problem, of course, is during training, we have access to these mini batches, and we can do we can calculate a mean and standard deviation over a mini batch of data. Usually at test time, we would think of getting only one data point in at a time. It's unlikely that in practice we'll really have access to a whole mini batch of test samples. So there's a trick to just get around that. Okay, so that is more or less the would have been the end of the lecture on training deep neural networks. So let's now move on to convolutional neural networks. So this is just basically an example of a specific type of deep neural networks that is very commonly used in computer vision applications. And so specifically, we'll look at one of the most simple computer vision tasks, which is to classify images into a number of predefined classes. Again, we'll think of this in the supervised learning setting, so we have access to data with labels. In the example I'm showing here, we have two classes. You can probably guess what the two classes are. And you can imagine we have access to a bunch of images that we know belong to class A. We have access to a bunch of images that we know belong to class B. We want to train a neural network that takes an image as input and then as output tells us in which class that image is. So this would be our training set, and then after training, we might want to give it an image like this that it hasn't seen before and ask it, is this part of class A or class B? Okay. And as always, we want this classification model or the classifier to be able to generalize, in other words, accurately tell us what is the class of this image or the label. Okay, it doesn't have to be 2 classes, it can be 10 classes, it can be 1,000 classes, doesn't matter. Of course, we want the training set to be representative of these classes, otherwise we'll be in trouble. And as always, we might evaluate the success to generalize on some holdout test set. Okay. Now, there's kind of an immediate problem with constructing a neural network or a deep neural network like we've seen before for this problem, and it really comes down to the dimensions of the input. So typically images, as you might know, consist of pixels arranged almost as a matrix in rows and columns. We want, for our neural network, the input should be a vector. Now it's easy to convert the pixels of an image into a vector. We can just stack all the columns below one another, or maybe all the rows next to each other. So we can convert all of these into vectors, but those vectors are then typically very, very large in dimension. As I say, we can flatten an image into a vector, either by rows or by columns. So that's fine. But even if we have only very small images, 256 by 256, that's super small by today's standards. This would give us, if you multiply 256 by 256, I hope I did this correctly, you might then get an input dimension of 65,000. And that's still okay. We can work with vectors of that size. But if we now have a densely connected hidden layer with only 1,000 nodes, so that's quite a drastic drop from 65,000 dimensions down to 1,000. Of course, if it's densely connected, it means all the nodes in the hidden layer are connected to all the nodes in the input layer. So we would then have 65,000 times 1,000, so it's over 65 million weights already to train just in that first layer. So we don't even yet have a deep neural network. We have very, very small images, so you can imagine the number of weights I would need if I'm using images as inputs can be quite high, very, very high. So what we'll do instead is to try and simplify the network a little bit by making some assumptions. The one assumption we'll make is to say that in an image we can think of objects having some kind of local spatial support. So if I'm trying to identify what's going on in this image, maybe I don't have to look at all the pixels at once. Maybe I can start by focusing on smaller parts of the image. And then maybe later on, as I have more layers, I can start combining those smaller parts. But certainly in the first layer, maybe I don't have to calculate activations based on all the pixels in the input image. The other thing is then translation invariance. Maybe if I have 3 images like this, they kind of all depict the same thing, regardless of where the object in the image is. This is, of course, is an assumption that's not always valid, but maybe for image classification, I can make this assumption. Okay. So how do we encode these assumptions into our neural network? And the idea is basically to go from a densely connected or a fully connected layer to something that we call a convolutional layer. So if we think of our image as an input to the neural network, a densely connected layer might take all these pixels in our input space. Can you see the cursor? And if these are the nodes in the first hidden layer, then maybe this node would have to be connected to all the pixels in the input. So instead of that, we think of this locality assumption. So every node in my in the output of my layer will only be connected to a much smaller localized region of the input image. So that's shown on the right there with the green thing. So this node is now not connected to all the pixels in the input, only to these 9. So we changed the fully connected layer to be locally connected, and every output node is now connected to only a local region of the input, which we call the receptive field. Then to enforce this idea of translation invariance, we'll say that different sets of connections have the same weights. So instead of saying that all these different connections have different weights, if this node in the output of my layer is connected to these 9, and this node is connected to these 9, then these 9 weights, they can all be different, but they'll be the same as these 9 weights. So different sets of connections will have the same weights. Okay. And as we'll see, it now also makes sense to think of the output of this layer no longer as a column vector of nodes, but rather also as a little matrix with rows and columns. Okay. Basically, as we move around in this little matrix of output nodes of this layer, we'll be moving this local receptive field along. Okay. And again, remember, just as in a normal neural network, we'll take the values of the inputs, so the values of the pixels in this image. I should show this one. And we're going to multiply each of those values by their corresponding weights, connection weights, and then sum them all together. We might have a bias as well, and then we would apply an activation. Okay, so that's still the same. So this idea of kind of sliding this local receptor field across this image and then calculating weighted sums based on the values of the pixels multiplied by the values of my little 9 by 9 window of weights. That is very much like the operation called discrete convolution. It's actually a discrete correlation, but for some reason the computer vision community decided to call it convolution. So as you might know, if you've done an image processing course or maybe something like Fourier analysis where you also use convolution, we have the convolution of our image F and our kernel K as basically a weighted sum of corresponding pixel values and kernel weights. Okay, but we don't have to dwell too much on this equation. The point is just that we have this little kernel or this little window that has weights, and we slide it across the image, and at every position we calculate the values of the kernel multiplied by the corresponding values of the pixels and sum them all together, and that gives us the value of our output at that location. The effect of this is some sort of heat map of similarity between the image and the filter. So here's an example of an image, and we compute a convolution with this little kernel or filter, and we might get as output this, and I don't know if it's clear on this slide, but basically the greater the value here, the brighter the value here is, the more that part of the image corresponds to this thing. So this kind of picks up all the A's in this image. Okay. Here's a small example just again to show this idea of convolution. So this is our input image. We would typically, if we're using a 3 by 3 filter, we would then pad this image with one column and one row on every side with zeros, because the filter is usually centered around pixels in the input. So of course, if we're at the corner or on the edge, we don't actually have values to the left and to the top of it. So we can pad the input with zeros, and then to compute the convolution, we basically slide this 3 by 3 window across the image at every position, like the one shown here. We would multiply corresponding values, so that 0 times 1 plus that 0 times that 0 plus 0, 0, da, 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 and we add them all together and then get maybe a 2 over there. Then we slide the filter one to the right, and again compute this weighted sum of the pixel values and the filter weights and get our value over there. The input is a kind of an X. There's just another. That I've showing in blue. The filter, you can see, is designed to kind of pick up this diagonal sort of structure of ones surrounded by zeros, and we can in fact see in the output it gives us a strong response around here, where in the input we do have that kind of structure. Okay, now so this is the kind of how convolution works. We have our input image, we have some small kernel or filter, and we will slide that kernel over the input and get as output. You can also think of that as an image of values. And this will now be the output of our convolutional layer. We can add a nonlinear activation to these values, and then it goes on to the rest of the network. The numbers in this filter are basically the weights that we'll want to learn during training. Okay, so these are the same as those connection weights that we had in our densely connected neural network. So again, we would have some image as input, and we want to learn an optimal set of weights here, so that when we apply convolution and get okay, sorry. Yeah, so we basically want to learn an optimal filter here. In a convolutional layer, we can also have multiple filters, not just one. So we can apply various filters to the same input and get a few of these outputs that we can then somehow concatenate and take further into the network. And in that case, we'll just want to learn an optimal set of these kinds of filters. Okay. So if we compare our normal densely connected neural network layer to a convolutional layer, we can see that the convolutional layer is basically just a restricted case of a fully connected layer. So what we're saying is that instead of each of these outputs being connected to all the nodes in the input of this layer, each output is now only connected to a few of them. In this case, only two. So that would be the receptor field. So that is the same as saying that we're forcing the weights of all the other connections to be 0. And that's the one thing. The other thing is that we then also force some of these weights to be the same, or to be shared, or to be tied. So in the case of this little convolutional layer, all these orange weights will have the same value, all the green weights will have the same value. So in effect, we're calculating the output here by considering the receptor field over here, only these two nodes. We're calculating this output by considering only these two nodes, and so on, and using the same set of nodes, that will, the same set of weights, the orange and the green, that will be our filter in the convolution. Okay. So over here we have, what is it, about 20 different weights to learn. Here we only have 2 weights to learn. So you can see why this would drastically reduce the number of parameters that we need to learn, and we now no longer have that problem that we had before if we have an image as input and then a few thousand nodes as output layer, that we already have millions of parameters to worry about. Okay. Usually in code, when we add a convolutional layer to our neural network, and I'll end again with an example, we'll have to specify a few hyperparameters. In a dense layer, we basically have to specify the number of nodes in the layer. Here we have to specify the number of filters. Do we want to slide only one filter across, or do we maybe want to slide 32 filters, or how many ever? We have to specify the size of each of those filters. Is it a 3x3 filter, or a 5x5, or a 7x7? It kind of makes sense to choose an odd number as the size of the filter, 3x3, 5x5, not really 4x4 or 6x6. Of course, because it makes sense to have a pixel in the center around which we can center the kernel. We also have to specify a stride, that is the size of the step between consecutive receptor fields. So in the examples I've shown, we've always moved the filter 1 pixel at a time. We can also decide to move it 2 or 3 pixels at a time if we want to. Then this idea of padding as well, we have to specify if we want to do 0 padding or no padding. If we do 0 padding, that would allow us to have, as in this example, so this additional boundary of zeros were added later. Our input really here is only 5x5. The 0 padding allows us to have an output that is also 5x5. If we don't do 0 padding, our output will become smaller, of course. Those are the hyperparameters. Then for a convolutional layer, we would have trainable parameters, and those would be the values in all the filters. So again, this is basically the weights in a neural network. And while we're training, the network will try and learn optimal filters, optimal values for those filters, to basically emphasize or suppress appropriate patterns in the image. Like in the example I showed, that small filter was basically designed to highlight diagonal edges. But of course, depending on what we actually want to do with the entire network, at the end of the day, learning, or the training of the network will determine what are the best filters to use. Okay, and then the output of a convolutional layer would be a number of feature maps. For every filter, if we have 32 filters, we'll get 32 feature maps, and that is basically the result of doing a convolution on the input with each of those filters. Then another sort of layer that is quite common in convolutional neural networks is called pooling. And the idea is basically to consider the input of the pooling layer, which might be the feature map output from a previous convolutional layer, and basically replacing small windows in this input by single numbers. So this is a way that we can downsample our feature maps. We might decide that we want to replace each of these small 2x2 windows by their average. So what is the average of 9 and 1 and 3 and 3? I think that is 4. So instead of this 2x2 window of pixel values, we just have that 1 for over there. And again, we have this idea of a stride. So now I might move my little 2x2 window 1 to the right, and then I consider this 1 and 0 and 3 and 4, calculate the average, I guess that's 2, and then move it 1 across again and do that. I can also have a stride of 2, and then I'll have a smaller output like that. Okay, so as I say, this is a way that we can basically reduce the size of these feature maps a little bit during training. One obvious reason for that is, again, just to keep the number of parameters that I need to learn small. And yeah, I guess it also allows us to the network to be a little bit more robust against small perturbations or noise in the input. So if I change these values slightly or maybe swap them around, the average is not that much affected. Another way of doing pooling is not to compute averages, but rather to compute maxima. And I guess the maximum is even less affected by small changes in the feature map. Okay, so there are again a few hyperparameters of this kind of layer. Do we want to do max pooling or average pooling? How big should the kernel be? In this example, it's 2x2. What should be the stride? In the one in the middle, the stride is 1, and in the one on the right, the stride is 2. And also, again, do we want to do some sort of padding as we do this? And this kind of layer has no trainable parameters. We'll just compute a maximum or an average, so there's nothing to train here. And as I said, this kind of layer is just something we insert into the network after maybe every few convolutions, just to keep the size of the feature maps small. Yeah, okay, so I said that. So now to basically build a complete convolutional neural network, we can, as I said, use the output of a convolution or a pooling layer to become the input of a next convolutional layer, and that is, of course, how we get depth. So we can stack these convolutional layers one after the other. And if we think we've done enough of these convolutional layers, we'll then flatten the output. So whatever we have at that stage, which can be a series of feature maps, we'll flatten that into a single column vector and then feed that typically through a number of dense layers. And depending on the task that we want to perform, maybe we want to do image classification, so we'll then have a few dense layers to map the output of the final convolutional operations then into class scores. So after these fully connected layers, we might have a final output layer. In the case of classification, we might want the output layer to give us positive numbers that sum to 1. So we would use something like a softmax activation again to accomplish that. And to train this thing, we would again define a loss. If we're using softmax for classification, cross entropy would work well. And we would minimize that with some variant of gradient descent. Okay, so this is an example that I borrowed from the internet. So it just kind of demonstrates how we can build a small convolutional neural network. There's our image as an input. It goes through a convolutional layer and produces a number of feature maps. Then there is ReLU. You might remember that's an activation function. So it basically replaces every pixel value in each one of these feature maps with the maximum of itself and 0. Then we might take this set of outputs here through another convolutional layer. Of course, this is just an illustration. The number of feature maps at this point might grow or shrink depending on how we, I guess it can't really shrink, but it can double or it can triple depending on how many filters we're actually learning at this layer. Here we're performing another ReLU activation, then a layer of pooling. I don't know if it's max pooling or average pooling, but it's something. Then another convolution, another ReLU, convolution, ReLU, another pooling, convolution, ReLU, convolution, ReLU, pooling. And then there might be a fully connected layer or 2 or 3 that eventually has a softmax output that gives us normalized scores over the possible classes. In this case, we have 5 classes, and this network is trained relatively well, I guess, so it gives a high score for the class car for this particular image. Okay, and that's a convolutional neural network. In some of the other lectures, you might see much more complicated architectures than this. I know Naila this morning mentioned things like ResNet and that. They have many, many more layers and quite a bit more complicated architectural designs. But so this is just a basic one. Just again then, how we might code a convolutional neural network using one of these amazing software packages in Python. Again, this will be a sequential model. So it's, again, a model where we feed in the input on one side and it goes through a number of layers sequentially until the end. Here I'm using the model.add function to add layers. It just makes the code a bit cleaner. So I start with a convolutional, a 2-dimensional convolutional layer. It will have 32 filters. I'm choosing a kernel size of 3 by 3, strides 1 by 1. So this is the stride in the x direction and the y direction. The padding parameter I'm setting to the same, which means that is like saying 0 padding to keep the dimension of the output the same as the input. I'm using a ReLU activation, and the input shape, you might remember, for the first layer, we usually have to specify the input shape. In this case, it's going to be an image of size 28 by 28 by 1, so it's a grayscale image, very small. I guess this network is set up to recognize imnist characters. That's a famous data set for images that are 28 by 28. Anyways, then we add a max pooling layer with this. And I'm specifying a size of 2 by 2. I'm not specifying a stride, so I'm guessing we're just using whatever the default would be of that. Another convolutional layer, this time with 64 filters, and another max pool layer. Then I do a flatten operation, which just basically takes whatever number of activation feature maps I have at that stage and flatten them all into a column vector. Then I have a dense layer with 64 nodes and ReLU activation, and then finally another dense layer with 10 outputs and a softmax. So this is clearly a classification model that will have as input 28 by 28 grayscale images and classify them into 10 possible classes. I could then, of course, set up my optimizer as we saw yesterday and do a model.compile and a model.fit on data that I've loaded from somewhere, and then I have my model. This model.summary is quite useful to do once you've set up your model like this. It basically prints out on the screen all the layers you have and the various numbers of trainable parameters and the size of the output of every layer. So that's kind of a nice thing to look at. Okay, so that's it for convolutional neural networks. There is, of course, a lot that we didn't speak about. This really was meant just to be a kind of a very simple introduction to deep neural networks. These convolutional neural networks, as I said, is a special type of deep neural networks. There are many others that we didn't get to, but yeah, I don't know if you have any questions. We have some time, so yes. That would be the very first parameter, this 32 and 64. For their dense layer, these numbers are, of course, the number of nodes that we'll have in those layers. So.
Thanks. Yeah, when you talked about early stopping and the validation data, a couple of years ago there was this paper called Double Descent, where basically it goes back up and then you get an additional performance boost. How in practice do you deal with that? Is there a way to deal with that in practice? Because I remember reading about it, then forgetting about it, and now I thought about it again, and I was like, yeah, how do I deal with that in practice?
That's a good question, thanks. If you train a neural network, you can, of course, monitor the loss. You can calculate the loss at every iteration, and you can plot a graph that basically moves as the network is training. And very often you see funny things happening. And I mean, it never looks as nice as this picture. As you say, the loss can go up, and then if you just train a little bit longer, suddenly it goes down again. So, I mean, one way of dealing with this is to realize that you are now at a point where the validation is starting to go up, but then you do keep on training and just maybe see what will happen if I do keep on training, but you keep a kind of a snapshot of the model at this stage. If you keep on training and it doesn't seem to improve, you can just go back to where you were there. I think they call that patience, early stopping with patience. Yeah, so just be a bit patient, maybe things will improve. Yeah, but again, unfortunately, with the way these things are and our understanding of them from a theoretical point of view, it's, again, I know not a very satisfying answer, but sometimes you just have to see what happens if I do train longer. Maybe I do get something better out of it. Of course, what I've also seen sometimes is that the moment you start training, all the losses just go up, and they don't seem to ever go down again. And then, of course, something seriously is wrong. Then you would have to start thinking about, okay, maybe I need to change my learning rate, or I need to debug my code, or something like that. Okay. There's one right at the back.
Hi, I just want to ask about batch normalization. There's one trainable parameter, I think it was the gamma parameter, it's also just a bias parameter, right? So what happens if you now apply batch normalization after a fully connected layer? Isn't that now, but that fully connected layer also has a bias parameter, isn't those parameters filling the same role and playing off against each other now?
Yeah, I understand your question. We'll have to go see, just carefully what happens in the mathematics. But let me think quickly. Not really. So the bias parameter would. Okay, yeah, I'm not really going to answer your question, but I'll say something that is kind of in the same sort of thing. So theoretically, batch normalization isn't really necessary, because all we're doing is shifting and scaling all the values we get at every activation, and of course, the appropriate combination of weights and biases can do exactly that. So I think what all that batch normalization allows us to do is to kind of force optimal means and variances in a much more direct way than what you could do if you didn't do batch normalization. So theoretically, you can get the exact same network just by training long enough and let the network figure out, oh, these are actually the kinds of weights and biases I need in my network so that I can get the kind of properties that batch normalization gives you. I think the point of batch normalization is just the way in which it is set up allows you to do that much quicker, much more robustly. You don't need to train for as long and let the network figure this out as a combination of many parameters. We just insert 2 parameters whose only job is to give you an optimal mean and variance. I hope that kind of says something.
I have a feeling that Ferenc might talk more about that tomorrow, Ewan, because I think if you do the batch normalization, it's very much like that factor 10 that he put in as homework for us, which he then mentioned can affect the training quite significantly. So I think it's a similar effect to what you get in batch normalization.
So convolution, I feel like the example of convolution networks always comes with classifiers. And can you actually use them for other stuff? And if you do, what do you change? Is it just the final layer that you change? Or is it something else that changes as well? Or and also if you could give some examples for what you can use them for, basically. Thank you.
Yeah, thanks for that question. So maybe we'll go to this picture. So you can almost think of a series of convolutional layers as turning an image input into something that is more manageable by a neural network. So in this case, we at the end added a few fully connected layers, like a normal standard neural network, and then a softmax to do our classification. So in a way, this allows us to do what we call representation learning. It turns the image into a useful representation, which again is just a vector of numbers. In this case, that representation is then used for classification. If you want to instead do something like object detection, you can again have a few convolutional branch out into a neural network that would not give you classification scores, but maybe bounding boxes around the objects in the image. Or you could, I think in the talk this morning on self-supervised learning, there were quite a few examples of different things you can do with images. Maybe add color to a grayscale image. Again, you would have a few convolutional layers for that, which changes the image into a series of feature maps. And often in that situation, you use convolutions to downsample the image into a lower dimensional representation or feature representation, and then use something called transpose convolutions or deconvolutions, I think they also call it. I'm not sure that's a good name. To basically upscale that vector again into an image that now has color added to it. Yeah, so if you want to do something like automatic image captioning, so from an image you want to generate a text description of what is going on in the image, you would have a few convolutional layers to process the image into some sort of, again, feature representation, and that feature representation can then feed into a language model or some sort of neural network structure that can generate words sequentially as a caption. Yeah, so no, there's many different applications for this, and I think also the one thing about these convolutional neural networks, if you set them up carefully and correctly, I don't know if that's even defined, what is the correct way of doing it, but if you do it well, they do really perform very, very well compared to any other techniques that we know about. I think vision transformers is kind of giving convolutional neural networks a run for their money at the moment, but certainly a few years ago, this really was state of the art. And if you came up with some sort of machine learning model or approach or technique to solve a certain task, and you didn't use this kind of thing, that would be the first question is, okay, but what happens if you use a convolutional neural net instead? Yeah, so I think they're very versatile, and as I say, these convolutional layers are really a way to convert raw pixels, which is very high in dimensions and contains a lot of ambiguity and noise and these kinds of things, into a vector representation that is somehow useful for whatever you want to do after that. Yeah. There's also something we didn't talk about is pre-training and transfer learning. So there are now quite a lot of pre-trained convolutional neural networks available that you can download. So this means it's a neural network with all the weights already trained on some task, and you can literally then chop off the last few layers and add your own layers and just train those new layers. So you basically use the convolutional base, or backbone they also call it, of this pre-trained model, and just train the few layers of whatever task you want to do. And that is also a very effective way of doing a lot of things. Okay. Good.
Any more questions? Okay. If not, then we will thank Willie and then a break until tomorrow morning at 9 o'clock. And then it is David Forsyth, and he specifically requested that we make sure that everyone has a basic understanding of neural networks. So he is going to use that and talk about autonomous cars. So thank you, Willie. Now everyone will be able to follow exactly. So thank you very much. This was Willie's last session. So let us thank you for that.